So welcome to part 4 of homework 1 for computational methods. In this part, we're going to vectorize the function that we did in part 3. So if you haven't seen that, I suggest go watching part 3 first. But we're going to vectorize that function and then use that vectorization to generate a plot of the helical pipe. So instead of like what we did in part 1, which was just a single helix, we'll get a whole pipe of radius 0.5. So here we are at the code where we left off in part 3. So we're going to want to do, let's just call it surf vector. Then there's a very handy vectorize function that's already built in, which you basically give it a function and it'll vectorize it with broadcasting, which allows for the functions to be repeated across whatever leading dimension you give it. So for us, our leading dimensions are going to be over time. It'll vectorize our function and get all of those surface values when we tell it to vectorize our surface function. So we are going to tell it to vectorize just surf. And I think we'll need a signature also. So sig G-N-A-T-U-R-E. And I think this goes to 3, which, oh, that should be in this. So this signature is necessary for it to work. And it's something that our professor discovered in class and was able to let us know how to make it work for us. Or, excuse me, there should be an equal sign. There. So then what we're going to do is we're going to do another one. We'll just do big S. And do that's equal to surf vector. Then we want to give its arguments, so we want to do t, and then none, comma, all, theta, and what this will do is this tells it that it wants our time and our theta values, so that when we vectorize it, we get both those values as the curve goes. And then now that we have that, we're going to want to pull out our 3 axes, our x, y, and z. And we'll do it to S. Okay, run that. All right, it's not happy. So what is it not happy about? So all right, what are we not happy about? So this says all right, so it's not happy with our variables. So I think actually we want t first, don't we? Yeah, we want our time first, and then we'll put theta second. So let's just flip these two. T first, theta second, run that again. All right, so it's not happy with this, presumably because as we vectorize it, it was going to be a little slightly lopsided. So what we're going to do is we're actually going to transpose our surface vector S in order to, well, we'll find out, won't we? Let's run that. All right, still not happy because. All right, so the issue is still with this guy. All right, so it's still not happy with this surface vector, and numpy. So numpy and jax. So maybe this is the issue. Let's try that. Let's try that. Okay, that was not the issue. The issue is still same error. So vectorize. So we're vectorizing this, in normal from this, normal tangent, normal. We're going to cross the. Oh, that should be an N. Huh. Still not the error. So what is the error? So maybe these should be brackets. Let's try that. Let's run that. Still not happy. What is it not happy about? Alright, so still the same error. Let's change all of these to JMP. Oops, no. Okay. We got a different error this time, so it's progress. So it's not happy with this division here. That's supposed to be this. So we have DFDT, we have DSDT. All right, so it's not happy about that. So maybe it's the fact that these aren't Jackson and pi. Don't think that's it, but let's give it a shot. All right, so it's not happy with this. We define that. We can maybe this is as simple as this just needs to be returned. Let's run that. Run that. Run that. Ah, it worked. Cool. So now let's actually take a look at let's look at what X looks like. All right, so it's really long. Let's actually look at how big it is. Really big. So it's a total of over almost 2,000 data points corresponding with as the curve goes down. Cool. So now what we're going to do actually is we're going to then take all those points, the x, y, and z, and plot them. So let's give it a try. So figure, so we're going to set it up similar to the way we did this one. So let's open this real quick. Just close this. So we're going to make a subplot. rows equals 1, columns equals 1. Now this is where it gets interesting, because what we're going to do is we're actually going to make two subplots. One that, well, that's where it's going to get interesting, because what we're going to do is we're going to actually, since we have both t and theta that we have now, we're going to use a for loop to kind of plot out these points. So first we'll do for I in range theta dot size. We're going to theta add scatter 3D x equals, what we're going to do is, since x is a big guy, oh, we looked at x right beforehand, and it was big, almost over 2,000 points. We're going to have to be very specific about which ones we want to use. So what we're going to do all the rows for each column I as we iterate. Then y will be the same way. So y equals y. Z equals z. I. Okay. Now what else do we need? So we need to change the mode to lines. Okay. Get out of that for loop. Now we're going to do the same thing using the other variable. So for I in the range of t dot size, we're going to add a second scatter. The same way. So x equal to x. This time we're actually going to flip we're going to pull the other values. So we'll do I comma colon y equals y, I comma colon z equals z, I comma colon. Let's make sure we got all that. And we'll do mode equals lines. Okay, so after we've done that, then we'll do fig dot update layout. We'll do width equals 600, height equals 600. So we're doing this so that all the width and the height are the same size. That way, when you can actually see the circle shape. Whereas normally it's not the same size, and it appears kind of like an oval, even though it is a circle. So that's why we're doing that. Then we're going to do template equals plotly dark. This way it's a bit easier on the eyes. Let's run that. Not very happy about that. So generals make underscore subplots. Fig equals make subplots. Voila, here we are. So now we have our thing. Should probably get rid of all these colors, huh? Let's get rid of the color by specifying line underscore color equals white. Do the same over here. That way it looks a little bit less busy. here we are. So now this is our, so we can actually zoom in and we can see different. Although, the circle are supposed to extend all the way up. Huh. Let's make this equal to t dot size. Let's see what happens. Excuse the long run time. There we go. So that causes all the circles to extend all the way up. And as you can see, we have our helical pipe following the same curve as in part 1. This time it has a radius 0.5. You can see the axes in this. So let's see if I can get the legend. Let's see. No, let's see if that works. Nope. It's not that way. So let's try show legend equals false. Show legend. Let's try getting rid of these. Lowercase. No. Oh, forgot the comma. Hey, it worked. Cool. Hopefully that should get rid of the legend, even though we have to wait through another loading period. There we go. So here's our helical curve. You can see the lines that make up it, going both along with the curve and also making up this normal and binomial connection point. And there's our curve. So we vectorize it, we plotted the helical curve, and there we are. So let's reset to default. There's our curve. And join me with me next time in part 5 to then look at, well, what if we wanted this instead of a curve, we wanted it in a straight line, straight pipe. So join with me in part 5 for that.